Today's lesson is really going to use several concepts that we've already discussed, and it's going to merge all those concepts together into a section we call compositions of transformations. So since we already have a lot of the parts to this machine, let's go ahead and jump right into an example. We're going to get a segment on the coordinate plane. We're going to want to translate that segment following the vector -1, 4. Then we're going to want to take that result and reflect that result over the x-axis and get yet a different result. So we're doing two different transformations to a pre-image, and that is what a composition of transformations is. So we've got our segment AB. When we translate it following that vector, we're going to get a segment A prime, B prime. And since that vector is -1, 4, remember that means the -1 means 1 unit left, and the +4 means 1, 2, 3, 4 units up. And there is our first image, A prime, B prime. However, then it says to reflect that new image over the x-axis. A prime is 1, 2, 3, 4, 5 units away from making a right angle with the x-axis. So let's go another 1, 2, 3, 4, 5 units away on the other side, and that would give us not A prime anymore, but A double prime. Let's do the same thing with B prime. That is going to be 7 units from the x-axis. So let's go 7 units below the x-axis and put our B double prime point there. And then we'll finish the job by connecting the 2 points and making our segment. So A double prime, B double prime is the result of a composition of transformations. Let's define that more mathematically. A composition of transformations, sometimes they'll just call that a composite transformation, when one transformation is applied to a pre-image and then another transformation is applied to that, just like we did in the example a moment ago. A specific type of composite transformation might be called a glide reflection. That's a type of composite transformation where the pre-image first gets translated, which means it glides, then that result gets reflected. And that is exactly the type of example that we just looked at a moment ago. There are other types of composite transformations. You don't have to translate and then reflect every time. What if you had a rotation followed by a reflection? Would that be considered a composition of transformations too? Short answer, yes. It's two different types of transformations being put together. Same situation, what if you really got crazy with it? What if you had a translation, and then a rotation, and then another translation? Yes, that would also be a composite transformation because it is more than one transformation being applied to a pre-image. This brings us to a theorem that's a little wordier. A composition of isometries. That's what we looked at in the example. A glide reflection, gliding maintains congruency between the pre-image and the result, as does reflection. So what we did is we took two isometric transformations and applied them to an object. The object didn't change size or shape the entire time. So the result was also an isometry. So if you apply an isometric transformation to a point or set of points, and then apply another isometric transformation to the result, you'll end up with an isometry in the end. Or, a little more quicker, the composition of two or more isometries will result in an isometry. And that is again what we saw in the example at the beginning of the notes. For example, you can take a triangle and if you rotate it any which way, that is still a congruent triangle to the pre-image. And even if you slide it, if you transform it, it's still congruent to the preimage. All right, let's look at the next theorem. It's a little more in-depth, but we'll start out by looking at a picture. So the pictures, I think, make the words not as scary. Let's start out with two parallel lines. Very easy to understand that. And let's take a triangle here, and let's reflect that triangle over that first parallel line. We're going to take this triangle and reflect it over this line. You can probably imagine what that's going to look like. Something like that. And then what we're going to do is we're going to take that new triangle and reflect it over the second line over here. And you'll notice the triangle is now back at least in the same orientation that it was in originally. There's kind of a weird phenomenon that happens. If you take a line and measure the distance perpendicularly between the two dotted parallel lines, what I'm going to do is I'm going to copy that line. I've got two line segments that are exactly the same length, and if I arrange them end to end, starting at the first triangle, notice where I end up at the same point on the reflected shape. We call this distance d. That makes this distance twice as much, so 2d. Also, the line segment formed with the d is perpendicular to the line of reflection, either line of reflection, really. And that brings us to our next theorem, Theorem 9.2, reflections in parallel lines. So the composition of two reflections over those blue parallel lines can be described by a single translation vector. If we kind of cut out the middleman and went right from here to there, you could say that the vector describing the translation is perpendicular to the two parallel lines and also twice as long as the distance between the two parallel lines. One more theorem to tackle here. Let's start off with another picture. This time we're going to have two lines again, but this time they're not going to be parallel, which means the opposite of parallel is intersecting. At some point these lines will intersect. So here's our first good old vertical line, and we're going to have another line that intersects it. What we're going to do is we're going to take some segment this time. We're going to reflect this segment first over the vertical line, and we're going to get something that looks like that. And then we're going to take the result, the segment we just got, and reflect that over the skew line below it. And we would get a final image that looks something like that. And lo and behold, if you kind of highlighted the point where these two lines intersect, right there, and thought of that as the center of a rotation, you would find that from the pre-image to the final image, going about the point of intersection, if this little angle here is x, you would find that the arc going from the pre-image to the final image would be twice as much. It would be 2x degrees. So in theorem form, Theorem 9.3, reflections in intersecting lines, the composition of reflections over two intersecting lines, different than Theorem 9.2 where the lines were parallel, can be described as a single rotation that first of all rotates about the point where the lines intersect, and second of all rotates over an angle that is twice the angle measure of the angle between the intersecting lines. So we'll be looking at some problems that deal with these composition of functions in the very near future.